Okay. Um, we worked in 10.1 was about testing the difference between means for independent samples. 10.2 was testing the difference between means for independent samples. Okay, the difference between those two sections was whether we had small samples, so we used a t-test, and we didn't know the population standard deviation, or we had big samples and we didn't know the population standard deviation, which we would use the z-test. Today we're going to talk about dependent samples. So I think for a lot of hypothesis testing, you like to maybe I just think that situations that maybe you're in or that you're going to be in the near future to see if something is creating change, this is a great tool to develop an understanding of whether what you instituted created change. Okay, so some of you might be part of athletic teams, right? Okay, let's say, or maybe a I don't know, some type of activity that you can get better at, okay, through practice. Okay, so I always go back to like athletic teams. Like if I have a let's just say a football team that's not very good, okay, and we institute a weightlifting program or a sprinting program or something like that, and we run through that in the summer. And then I want to say, okay, how can I judge whether that was effective or not? Did it make better athletes? It might not show it in wins and losses, but did it make better athletes? Okay, we can do this type of thing. Okay, so basically what happens is that we start with, and I like to do it with looking at just like classroom scores, okay, or classroom grades, or do a pre-test on. Let's say that there's 14 of us in here. And let's say that we have a new section coming up or a new chapter coming up, and I pre-test you on it, okay? And now some of that stuff you might be familiar with, some of it you're not, but you test on it, see what your score is, and then we run through a treatment, which is the lectures of that chapter, and we take a post-test. What we can do is we compare your score on your pre-test to your score on the post-test, right? Now, you might do better, but your neighbor might do worse. And then your neighbors might do better, and that person's neighbor might do worse. Does that kind of make sense? So collectively, some people are doing better, some people are doing worse, some people are staying the same. And what we can do is we can do a dependent hypothesis test, okay, because those samples would be dependent because you can match your first score to your second score. Does that make sense? And you can see then collectively, did the treatment that we employed collectively for the course, for the class, did it benefit the class? Does that make sense? Okay. And you can see some of the examples I have down here kind of target that idea. So what we're going to do is make sure we have dependent or matched / paired samples. Okay. And you're going to see these three terms being used interchangeably. Okay. Sometimes they'll say dependent, and it's very obvious then what we're dealing with. If they say matched or paired, and that's what a lot of your statistical packages will say is matched or paired, it means the same thing, that they're dependent. Okay. If I want to do a hypothesis test on dependent samples, what we have to do is first realize that they are paired or matched. So your score will be matched to your pre-test score will be matched to your post-test score. Maybe we do an example down here that talks about wearing a particular type of shoe to increase your vertical, okay? So you'll do your vertical before you wear this shoe and then after you wear this shoe, okay? So you can be paired or matched. Your data can be related to one another that way. What we do then is we take and find the difference in that one particular pairing, okay? So maybe D is Lucas's pre-test, post-test. Maybe D is Peyton's pre-test, post-test. And then we find a bunch of these Ds for difference along the whole group. So maybe we find 14 of those. Does that make sense? Then what we do is we take those 14 differences and we average them. So this is called D bar, okay, which is the mean of the differences. Okay. That mean of the differences is approximated using the t-distribution if these three things are true. Samples are randomly selected. Samples are dependent, okay, which is hopefully obvious. And then both populations are normally distributed, okay? When that happens, the t-distribution will approximate the distribution of these differences, okay, this mean of these differences. The degrees of freedom is n minus 1 like it usually is for the t-distribution, okay? Some symbols here that we use through this testing. N is the number of pairs of data, okay? D, obviously, is the difference between entries for the data, okay? So if there's 8 pairings of data, there's going to be 8 differences. If there's 12 pairings of data, there's going to be 12 differences, okay? Mu sub D is the hypothesized population difference, okay? Or the hypothesized differences of the paired data in the population, okay? D bar, we already talked about that, that's the mean of these differences. And then our standard deviation, which is S sub D, the standard deviation of the differences between the paired data entries, is this. And this is the exact same thing that we've talked about back in chapter 1 with standard deviation. We had a formula, this was X, and this was X bar, okay? But now X is just the difference between your paired data, and this is the average of those differences, okay? So you can use this formula. So you'd find each one of those differences, which is kind of weird to say because it's differences of differences, right? Okay. But then you would square that and add all those together, okay? And that is usually the formula that you get initially. That's kind of referred to as sometimes as the analytical formula, but it's not the most appropriate for calculations. This, after we do a little bit of, essentially all we do is distribute here, use some summation formulas, and we get down to this. This is what we call the computational formula for standard deviation. We talked all about that in chapter 1, which I know might seem like a year ago. We're not even going to run through this by hand. Okay, we're going to use Excel to do this for us, but if we had to do it by hand, we would just take the differences squared and add all those together. Then we take the differences and add those together, then square that, divide by how many pairs we had, and then divide by our pairs minus 1. And that'll give you my standard deviation after I take square root. We're going to use Excel initially here to help with that, okay? So what I want to do here is get to an example, okay? The test statistic that we're going to use is D bar, okay? Which is the average of the sample mean, or sorry, the average of the sample differences, or the paired differences. And then once we have that, we're going to standardize that down to a t-value. So we take t bar, so again, it's your observed data, your observed mean in this case, minus the hypothesized mean or the expected mean, divided then by standard error. And this is how I find standard error for a t-distribution. Okay, so it's a formula hopefully that we have seen before. Okay, we have seen it usually with like x bar minus x or mu over standard deviation divided by radical n. Okay, but that is very similar to what we saw in 10.2, I think 9.2. We've seen this formula before with the t-distribution. Okay. We're going to do this by hand, and then I told you this yesterday. For the remainder of the course, we'll do at least one of these problems by hand, and then I'll show you a variety of ways of maybe capturing that same information using technology. So I'm in the first class because it might be seeming like we're bouncing around from GeoGebra to Excel to StatCrunch to anything else that I might find that might be appropriate. Okay. And they're like, well, when we get to a test, will I be required to use every one of those? I don't care if you use any of them. If you want to use just the formulas, do everything by hand, have at it, okay? If you're a person that relies solely on GeoGebra, have at it. What you need to know, though, is GeoGebra has its limitations. If you're a person that wants to work solely in Excel, have at it, but know it has its limitations. If you want to do stack crunch, have at it, but know that it has its limitations. Does that make sense? And if I know one program's limitations, then I can use it in tandem with another program that picks up the slack of the first one. Does that make sense? So I use 2 or 3 programs to get the job done. Okay. I like to use free programs. Okay. There are a lot of, SPSS, I said, is IBM's. You got to pay for that, and it's pricey. The StatCrunch is pricey as well because you have to have the Math Excel subscription to get access to that. You could probably purchase it standalone, but if I was going to purchase a stat package that is standalone, I probably don't go with something like Pure. I'd probably go something with a little bit more robust like SPSS or something else, okay, that is designed solely for like research. There are packages out there. If you just do a quick Google search of like free stat package, okay, you'll find something that will probably accommodate your needs for the most part. Talked about as when we get to college and have to use this stuff maybe in a course, if you have to write a research paper or conduct a survey or something like that and provide the data, you'll have that. You won't have to go out and buy things on your own. The university will have subscriptions that you can use. Does that make sense? But they're going to be, and you don't know what you're going to get. You might go to, I forget what it was. I used a different program at Bluffton, and then I went to Dayton and had to use SPSS in Dayton. Okay, and I had no experience with it. But what I learned at Bluffton allowed me, whatever that program was, allowed me to kind of understand and navigate SPSS a little bit. Does that make sense? Using Excel is going to allow you to kind of navigate all of them because they're very similar structures. So this question, you guys ever seen shoes like this? Have you? Okay. So these are called strength shoes. They were big in the 80s, started in the 80s. They got real big in the 90s. When I was in school, I had a kid in my class. He would wear these to everything. He'd wear these to school. He'd wear them to all our practices. He would wear them to everything, like wear them to church. They didn't help him. He was still he was really trying to get his vertical fixed and his speed fixed, and it didn't help. But my friend worked so often that he would walk around. Yeah. And that's what they're designed to do, so that they isolate your calf muscles and you increase your vertical, that kind of stuff. But they come with like a workout program. They come with like back then it was a VHS tape, and you did their exercises with them. Okay. So we want to see, and this is the idea that I was talking about, like if I wanted to see if there was a improvement with athletes in regards to like strength after I put them on a like an exercise program, okay, or is there improvement in an individual's cholesterol levels when I put them on a diet or something like that? Does that kind of make sense? So we can compare them before and we can compare them after. I don't know. So here it says in the 1980s exercise shoe called strength shoes put into circulation. Manufacturer claims that athletes can increase their vertical jump heights using the manufacturer's shoes. The vertical jump heights of 8 randomly selected athletes are measured. After the athletes have used the shoes for 8 months, their vertical jump heights are measured again. The vertical jump heights in inches for each athlete are shown. At alpha being 10%, is there evidence to support the manufacturer's claim? Assume the vertical jump heights are normally distributed. So what we have to do here is realize that we are dealing with difference of paired or matched data, okay? So what I want to look at here, and this is the way I've written it down below, but you have to decide this before you do it. How are you going to conduct the differences, okay? So I'm going to, I think the way I've got it written down below, I'm going to do the vertical before minus the vertical after, okay? So what that means to me is that the, if I go use mu because that's the mean of before minus mean of after. Okay, now think about this. If I have a value of before, which is 24, minus a value of after, which is 26, what kind of number is that going to be? It's negative 2 in this case, right? It's negative, okay? Would that, for that one person, would that show that there was an increase in their vertical after using this? Does that make sense? So what that shows to me is that if I get a negative value back, if I did this with all of these data pairs, a negative value back because of the way I did the subtraction would indicate that there is an increase in their vertical, which would be the fact that if mu of the differences, if the average of the differences is negative, meaning less than 0, that shows that there was an increase in their vertical. Does that make sense? Okay, so I'm going to say that that's my claim. Okay, because that's what he says. He says there's a claim that their vertical jump increases. And the way I can write that, if I use this type of subtraction, is that mu sub d is less than 0. That is actually an increase because the order that I did subtraction. Now, if I did it as after minus before, okay, so if we go after minus before, then you're going to get what kind of number? Positive. So then I would say mu sub d is greater than 0. Okay, and that will then change my null hypothesis that goes with it. Does that make sense? So you may, just depending on the way you think you're going to do your subtraction, you may have completely different work and structure than your neighbor. But it should all work out in the end to give you the same t-values. You might have a left-tailed test, but they've got a right-tailed test, that kind of stuff. But we should still arrive at the same conclusions. Okay, so I want, maybe if we have time, we will go through and do this both ways. Doing before, record that data, see what we get, before minus after, and then do it with after minus before. Okay. Another way of doing so, this would say that mu sub d, if this was less than 0, this would be greater than or equal to 0, right? So that is the way that you're going to most commonly see the hypotheses established in this type of testing. If you come down here, I've got the options here for you, okay? The idea is that and you can start this way if you want to, if this makes most sense to you. We are saying that after the program, your average should be greater than it was before, right? So the mean before is less than the mean after. If I subtract those, I get this here, okay? And that's exactly what I did earlier, before minus after. And you see that that would be less than 0. So that's going to be a negative number, which was the negative 2 that we realized above in that specific example. And if you want to write that, so mu of before minus mu of after, that is mu of your differences. Okay? So those three structures right there are all appropriate. Okay? But this is the one that you usually come across. And I show you these two, and I show you what we did up here, because I think it's really hard to read a scenario and think, okay, well, I want to increase my vertical. That's the claim. Why is this talking about less than, right? And that's the reason, okay? It's because the order of subtraction that you do with your data here, okay? Is everybody okay with that idea? All right, so now, if we go through this, if we're doing it by hand, okay, we want to find the differences. So we want to find D, okay? So the difference between this, and I'm going before and after. And the reason I decided initially to go before and after is just because of how I organize my data in the table. I just want to subtract straight down. So 24 minus 26 gives me negative 2. This gives me negative 3, 0, negative 1, 2, negative 2, negative 5, negative 3. Okay? So that is our set of differences. Now we need to find D bar, which is the average of those 8 differences. Okay? So I think might as well just establish this stuff in Excel real quick. Do you guys want to run through the standard deviation formula by hand? Probably not. So let's go ahead and do this. Let's go I'm just going to type it in. I'm going to type this one in column A. I'll type this row in column B. 24, 22. All right, so I typed those in. Don't worry about the second column where it's putting 0.00. I formatted the columns earlier and for a different application, and just I didn't unformat those, but it doesn't matter. So now those are the eight objects in our sample, okay? And they're paired. This was person 1 before and after, person 2 before and after, and so forth, all the way through person 8. If I want to find the difference of those, it would be the way that we did it, A1 minus B1. We got our -2, drag that down, and we see all those other differences that we calculated, right? Okay, so you can do it by hand or use Excel. The reason I want to use Excel is because I'm going to have to find the average of those differences. So I could do it by hand, -2, -3, -1, +2, -2, -5, -3, and then divide that by 8. Or if I'm on Excel, I could just say equals average of C to C, -1.75. Okay, is that doable? So D bar is -1.75. All right, so now we want to figure out what T is. Okay, remember T is D bar minus mu sub D divided by standard deviation of the differences divided by root n. Okay, D bar -1.75. Mu of the differences, the hypothesized mean of these differences, again, as always, is right there. What is that value? 0, right? Okay. So when we find these differences, because the alternative hypothesis, once we realized how we had to structure that, then told me what the null hypothesis was, because it's the complement. This null hypothesis is always going to be 0 here, meaning this is always going to be 0. Then we're going to divide that by the standard deviation. Now, I don't have that number yet, but then we'll divide by the square root of 8. We need to find the standard deviation. So I'm going to hit equals standard deviation dot. Now, am I dealing with a sample or a population? Sample. Okay. So now remember, it's the standard deviation of the differences. So I'm going to select those, and I get that number right there. Okay. So 2.12132 is then that T value. Is that okay with everybody? Okay. So now we're going to run that through and figure out what that calculates to be. So we're going -1.75 divided by 2.1213 divided by square root of 8 and -2.3 repeating. Okay, so that's my T value, -2.33. And what we find out, because we rounded this standard deviation, right? You'll find out if you don't round that, this stays -2.3333333. But regardless, doesn't matter. So that's our T value. Does that make sense? Okay, so that is what we are going to compare to our critical values. Okay, now our critical value, think about this test. What kind of tail is this? It's a left tail. Okay, we had an alpha of 10%. Okay, so we're going to look at that being 10%. Okay? We have to figure out what is the t-value that establishes that 10%. So again, in Excel, I'm going to hit equals. Now you can use tables and all that kind of stuff for this. I think it's just easier. T dot dist. Okay. Our x value. Oh, I'm sorry, I got that backwards. I was thinking p-value. We want t dot inv, which is probability. So there's the alpha of 10%. And our degrees of freedom is n minus 1. So n was 8. And we'll get negative 1.414. Okay, so that's negative 1.414. Where does our t-value of negative 2.33 fall in comparison to that number? Falls to the left, right? Okay, so it falls over here. Okay, so if that's negative 2.33, what do? We reject. We reject the null hypothesis. Okay, so if I reject this, then we would say that we have sufficient evidence to support this, which was the claim, right? And in words, the claim was that you increased verticals. So we have sufficient evidence from the data that vertical heights do increase through the use of these shoes. Okay, which would be a nice marketing tool for strength shoes, right? Okay. Now, would you agree that's a lot of work? Okay. I think we could probably handle it. We could talk even further. Okay. What is the area right here called that is attached to that negative 2.33? That's the p-value. Okay. And that p-value is less than the black area, right? Now we could come to this and say, okay, if I want t.dist of negative 2.3333 repeating, degree of freedom 7, and say true, that area is 0.0262. Okay, and that area then is less than 10%, which was my alpha, right? So p-value less than alpha, you reject. Same argument. Okay, what I want to do with you right now is to show you and get you guys to use this as well, StatCrunch. So we opened this up yesterday, right? Okay, so if you go back to StatCrunch, the nice thing about StatCrunch is that and then all your other, because Excel is not built solely for statistics, right? There's a lot of different applications for Excel. So when we want to provide headers for our columns in Excel, we have to tell, when we run our statistics package on it, we have to tell it whether we have headers or not. Okay, whether we have items that are describing our lists. What's nice about all your other statistical packages that are dedicated just to statistics and no other purpose, okay, is that they allow you to change right here what your headers are for each variable. Okay, so all I've done here is I clicked on that, typed in before, clicked on that, typed in after, and I plugged in my data. Okay, is everybody okay with that? All right. Now, what we're going to do is we're going to go to Stat, and here's where we still have to understand our mathematics. We have to understand what we're really doing, because there's a lot of options here that I could pick. I have to know the scenario, establish that I was going to use a t-statistic, okay? And when I open that up, it gives me these options. And we talked about these yesterday. This was like chapter 9, if I had to do hypothesis testing with one sample or a confidence interval with one sample. Here's working with section 10.1 and 10.2. Okay, working with two samples that were independent. These are dependent. And remember I said earlier that we had to know that dependent can be described as matched or paired? This is why. Because if I just say dependent and I go through here, this program doesn't use that word. Okay? We have to know it means paired. So I click on that. And now it's pretty user friendly. It says select sample 1 in what column? Well, sample 1 for us we did before. Okay? So if I didn't rename those, it would say VAR1 and VAR2. Okay. Now I'm going to go to column 2. Sample 2 is the after. Okay. Now this where stuff, I'm not sure, because I don't use StatCrunch very often. I'm more of an Excel person. I'm not sure what all this optional things are. So if it's optional and I don't have any information in my problem that maybe leads me to changing any of the structures, I'm going to leave them alone. Okay, so let's leave those alone. We could save the differences. So basically just take the subtraction. These will probably put them into another column for us if we wanted that. I don't care about that. We come down here when we want to perform. Do we want to do a hypothesis test or do we want to do the confidence interval? We want to do hypothesis testing, right? And this is why it's important. If you go back to here, okay, when we introduced this, I said that there are 3 different ways you could write your hypotheses, right? Okay, but only one of those ways, which was the one that we ended up using, is demonstrated here. This is auto-filled, right, as mu sub d. Capital D, they're using as the difference. So if I look at my hypothesis here in the alternative hypothesis, we're going to have to make that a left tail, right? The top is already established. That's always equal to. Okay. And I'm just going to hit compute. And does it give me, it shows me how I did the differences. It shows me that average of the differences, shows us the standard error, degrees of freedom, gives the t-test that we found, right? We found negative 2.3 repeating, and it found the p-value. Okay. Now, if you wanted to do critical values, if you wanted to establish whether I reject or fail to reject using critical values, you still got more work with the alpha being 10%, right? But what is the most important number in this table right now in order for me to efficiently make a decision on the null hypothesis? P-value. That thing right there. Once I have that, now I can compare that to 10%, 5%, 1%, whatever I need to, and make a decision on our null hypothesis. In this case, we end up seeing 0.0262, which was exactly the same thing that we got here in Excel. But you can see that there was less stuff we had to actually organize if we're going to use this program, right? Okay. Again, I don't care what you use. What I care about is that you get down to that and are able to effectively then decide, do I reject or fail to reject the hypothesis? Does that kind of make sense? If we, let's see if I can open another one of these real quick. Okay, so let's do, I don't know, so it's nice that it saves information. So what I'm going to do here real quick is say, what if my neighbor went, and instead of doing before minus after, they did after minus before. Does that make sense? So I'm going to say sample 1 is that. Sample 2 is that. What they would do then is that they would have a right-tailed test. Does that make sense? Okay. And if I compute, okay, this is after minus before. See if I can, I don't know if it'll let me open these at the same time. Awesome. You see here that I did, you have a left-tailed test there. Here's the right-tailed test. Okay. Here we did before minus after. Here we did after minus before. Now the mean, this was negative and this is positive. Okay. My t statistic is different. One's negative, one's positive. But are the p-values identical? So if the p-values are identical, then will I still make the same decision on the hypothesis, the null hypothesis, regardless of whether I went before minus after, after minus before? That kind of makes sense? So what I want you to understand is that your neighbor you might be working with somebody and they do it a little bit different than you. That's okay. All right? As long as you both arrive at the same p-values, you're going to make the same decision. Okay? Next 3 days, got 2 hour delays. My plan is just to kind of mess around with some of this stuff using these different programs. I believe, and I have to double check, but I believe Excel has a paired samples applet or function that we can address and see if we end up getting the same results there. GeoGebra does not have the ability to do this one. Okay, it probably has the ability, but it's not programmed to do it. So you don't have that at your fingertips with GeoGebra. No new homework.